Welcome to Lecture 15, whose subject is rotational motion. Like the motion of systems that we dealt with in Lecture 14, this one is a lecture in which we could either decide to apply Newton's law to every single particle of a rotating system, and we'd be here forever, or we could get clever and treat these rotating systems in interesting ways. And so let me show you a collage here of some examples of things that rotate. I've got an ice skater in a really neat view from above. I've got a circular saw blade. I've got our planet Earth rotating about its axis. I've got some wind turbines rotating. I've got the second hand, the hour hand, and the minute hand of a clock rotating. The compact disc rotating in its player, and the wheels of an old-fashioned steam engine. All these are systems that are undergoing rotational motion. And we'd like to find an easy way to describe that rotational motion. The way we're going to do it is by developing quantities that are analogous to the quantities we already understand for straight line motion. That is, quantities that are analogs of position, velocity, and acceleration. So what are some of these quantities? Well, let me give you examples. We need rotational analogs of position and change in position, that is displacement, of velocity, and of acceleration. So here I've got a picture of an object that's rotated through some angle, which I'll designate delta theta. So it's a disc or wheel or something, and it started out with that dashed line horizontal, and now that dashed line has rotated through an angle delta theta. Theta, the angular position, is going to be our analog of position, and therefore our analog of displacement, delta x, change in position, is going to be angular displacement, delta theta. You could measure it in revolutions, you could measure it in degrees, you could measure it in radians. More on radians in just a moment. What's velocity? Velocity is the change in position with respect to time. Delta x over delta t for straight line motion. Angular velocity becomes, therefore, delta theta, theta the symbol for angle, over delta t, the rate of change of angle. And I'm going to give angular velocity the symbol omega. Omega is the lowercase Greek letter omega. It's not a W. When my students come into my office and say W, I correct them. It's omega, lowercase Greek omega. Of course, there's no physics in that. That's just a convention. How would you measure velocity? You could measure it in revolutions per minute, RPM. That's a very common measure. I bought a new drill. It spins at 3,600 RPM or whatever. We could measure it in degrees per second, a less commonly used unit, or we could measure it in radians per second. Again, I'll show you in a minute why we might want to measure things in radians. What's acceleration? Acceleration is the rate of change of velocity. A equals delta V over delta t, so angular acceleration becomes the rate of change of angular velocity. Acceleration, alpha we're going to call it, is delta omega divided by delta t, the rate of change of angular velocity. Could be measured in revolutions per minute per second, RPM per second. It could be measured in degrees per second, or degrees per second squared, or it could be measured in radians per second squared, which has the simple abbreviation just seconds to the -2. What is this radian thing? Let's take a look on the big screen here, our math screen. What is this radian? It's the natural measure of angle. It also happens to be the official SI unit for angle. What's a radian? It's the ratio of the arc length to the radius on a circle, or a circular arc. It's a dimensionless quantity because it's a ratio of one length to another. That's why I can say radians per second is also just seconds to the -1, 1 over seconds, inverse seconds, because it's dimensionless. 2 pi radians in a full circle. That's because the circumference of a circle is 2 pi times its radius, and this is the ratio of arc length to radius. 1 radian is therefore 360 degrees divided by 2 pi, and that's about 57.3 degrees. Here's a picture showing how you develop a radian. Here's some angle theta. What is that angle? Well, I form a circular arc of which these white lines are the radii. Radius r, the arc has some length s, and by definition, the measure of that angle in radians is the ratio of arc s to radius r. And it turns out that an angle a little less than 60 degrees, 57.3 degrees approximately, gives me an angle of 1 radian. There are 2 pi of them in a full circle. That's what a radian is. Having said that, we can now make a relationship between rotational and linear velocity. Here is an object rotating with some angular velocity that I just introduced, which I'll call omega. If I am some distance out from the center of that disk, that point is going to be moving with some velocity which I designate v1. in a direction perpendicular to the radius at that instant. Go twice as far out, and the velocity becomes twice as big. This point is moving faster than this point because it's got twice as far to go, and if the whole disk is rotating with a common angular velocity, then it's going to take twice as long for this outer point. It's not twice as long. The outer point's going to have to go twice as fast to get around in the same amount of time. And so from that we can conclude that the velocity of a point some distance r from the center of a rotating object, all rotating with angular velocity omega, is simply omega times r. And so the entire object, when it rotates, does so like this. Those two velocity vectors going around and around, always perpendicular to the radius, and around they go. So rotational and linear velocity, the straight line velocity of objects on the rotating disk or whatever it is, are related by the straight line velocity is omega times the radial distance from the center. So now we have analogs of position, displacement, velocity, and acceleration. The next thing we need is an analog of mass. And to get an analog of mass, I'm going to bring in our volunteers, Laura and Jen. And I'm going to hand you these two rods, which are identical except for color. And I'd like Jen to heft that one, and I'd like Laura to heft that one. And then I'd like you to exchange them and heft them again. And would you say they have about the same mass? Yeah. Okay, now you stand still a moment, Jen. And Laura, what I'd like you to do, are you right-handed? Yes. Good. I'd like you to take that rod and just kind of twist it back and forth like this with your wrist. Okay? Jen, I would like you to do the same thing. Is that hard? Why can't you do it as fast as Laura? Are you some kind of wimp? Laura, why don't you do yours fast, as fast as you can. Both of you do them at the same time. What's the matter, Jen? Okay, so why don't you exchange them one more time? And try the same thing. Okay, excellent. So they look the same. They have the same mass. Thank you, ladies, very much. I appreciate it. What's different? What's different about these two rods is the distribution of the mass. In the red one, the mass is mostly concentrated down here where my hand is. And I don't have to move a lot of mass very fast at the ends of the red rod. The mass, the same total mass, is distributed very differently in the blue rod. In the blue rod, it's mostly up near the ends. And therefore, it's hard for me to make the blue rod accelerate. It has a lot more of a certain kind of inertia, not just straightforward inertia to changes in straight line motion. It would take the same force to accelerate both of them in a straight line, but resistance to change in rotational motion. It's much harder to change the rotational motion of the blue one than of the red one. And we call that resistance to changes in rotational motion rotational inertia. We're going to give it the symbol I. The term rotational inertia makes a lot of sense. Rotational inertia because it's a resistance to changes in rotational motion. Let's look briefly at what some rotational inertias look like. So here's a table listing the rotational inertias of some simple objects. To calculate these requires calculus, so I'm simply going to give you the results. On the left side of this table, we have cylindrical-shaped objects. The upper one is hollow, so it's a ring-like structure. The bottom one is a solid cylinder. The upper one has a rotational inertia given by its mass times the square of its radius. The lower one has a rotational inertia given by half the mass times the square of the radius. And the reason for the difference is that some of the mass of the lower one is down closer to the center. So like the red wand, it isn't as far out. And so it's not as hard to change its rotational motion. And therefore, its rotational inertia is less. On the right-hand side, we have a hollow sphere and a solid sphere. The hollow sphere, the rotational inertia turns out to be 2/3 of the mass times the square of the radius. In the solid one, it's only 2/5 of the mass times the square of the radius. It's less in the solid sphere, again, because more of the mass is concentrated closer to the center. So now we have in rotational inertia the analog of mass. And the next thing we need is the analog of force. What's the analog of force in rotational motion? Well, let me do a little demonstration that will convince you what that is. So here I have a great big thick lag screw, a 1/2-inch lag screw, and a 15/16 wrench, which I'm going to use to try to tighten this lag screw into a 2x4. I just can't do it. I can hardly budge it. Why? Because I'm not very intelligently pulling on the wrench right down here near where the bolt is. It would make a lot more sense. I'd be a lot more effective if I reached way out here on the end of the wrench and gave it a good yank. Okay. Now, reaching out on the end, I can turn it. And so the effectiveness of my applying this sort of twisting force, if you will, to this bolt is increased if I move out further. And you know that already. If you try to go through a large door, you push it as far away from the hinge as you can. You don't push it right near the hinge because you'd have to push a lot harder. We're talking about the effectiveness of forces in causing rotational motion, and the effectiveness depends on two things. It depends on how large a force I apply, but it also depends on how far I apply it from the point at which I want to make something rotate. That twisting force that I get by applying a force at some distance from this pivot point is called torque. And torque, if we want to get specific about it, is measured by the strength of the force and the perpendicular distance, which on this diagram shows as that line marked L, from the pivot point to the point where I apply the force. So if I take a perpendicular line, perpendicular to the force, and draw it so it intersects a line running from the pivot parallel to the force, that line marked L is the so-called lever arm, is the distance I use in computing the torque. The torque is that lever arm L times the force I apply. So the bigger that lever arm is for a given force, the greater the effectiveness at my ability to change rotational motion. So now we have torque, the rotational analog of force. So some other rotational analogs. Well, we had Newton's second law, F equals ma. Well, we've now got the analogs for force, for mass, and acceleration. So the rotational analog of Newton's second law is going to read torque, the analog of force, equals I, rotational inertia, the analog of mass, regular inertia, if you will, times alpha, angular acceleration, the analog of regular acceleration. So there's one rotational analog, the analog of Newton's second law. We have kinetic energy, K equals a half mv squared. We discovered that when we worked out the work energy theorem. Kinetic energy, a half mv squared. Well, let's form the analog of that for rotational motion. We'll call it rotational kinetic energy. Sometimes regular kinetic energy is called translational, meaning moving from place to place. Rotational kinetic energy, K sub rotation, is a half times the analog of mass. The analog of mass is rotational inertia I, times the square of the analog of velocity. The analog of velocity is angular velocity omega. So rotational kinetic energy is a half I omega squared. Momentum, P is mv. We've been talking a lot about momentum when we talked about systems. P is the mass of a particle times its velocity, or the mass of an entire system times its center of mass velocity. The analog is angular momentum. We're going to give it symbol L. L is the analog of mass, that is rotational inertia, times the analog of velocity, that is angular velocity omega. I should add a word of a caveat here for those of you who might be engineers or physicists. It is in fact the case that L is I omega only for objects that are fairly symmetric in the way they rotate. So that isn't quite universally true, but it's pretty close for simple objects. In fact, it's exact for simple objects like rotating wheels and rotating spheres and things like that. So more rotational analogs of the energies we've been talking about, of Newton's second law, and of momentum. So we have a lot of rotational analogs of the quantities we already understand how to use in linear motion, straight line motion, or motion along straight paths, or even curved paths in several dimensions, but not rotational motion. Now we're talking about rotational motion. So now we have rotational analogs of many of the quantities and many of the laws we already know how to apply to straight line motion. Things get interesting when we have combinations of both forms of motion. And I'm going to do an example of that in a minute, but before I do that, I have to discuss a special case of motion, and that's rolling motion. So let's take a look on the big screen here at what happens when an object rolls. Rolling is a combination of translational motion, motion from place to place, and rotational motion about some axis. Here's a way of looking at rolling motion. Here is some kind of object that's rotating. Maybe it's a simple disk or a wheel. It's got a center of mass, and you can think of the entire object as moving to the right with the velocity of the center of mass, which in this case is the point right in the center. So if you just think of the translational motion, the disk is just moving to the right, and all points on the disk are moving with the velocity of the center of mass. But if the disk is rolling, it also has rotational motion. So the second picture is pure rotation. In pure rotation, each point on the wheel is moving tangent to its particular point on the wheel. The point at the top is moving to the right with, in fact, the velocity of the center of mass. The point here is moving down. The point at the bottom is moving backwards. The point on the left is moving upward. Rolling motion is the sum of these two. Motion of the center of mass plus motion about the center of mass, that's the rotational motion, equals the rolling motion. And if we put all that together, here's what we find. The center of mass is moving at v sub cm, the velocity of the center of mass. The point at the top of the wheel is moving at the center of mass velocity plus the center of mass velocity, twice the center of mass velocity. The point here on the right is moving some combination of its downward motion and its horizontal motion associated with the motion of the center of mass. Point on the left is moving diagonally upward. Of course, as the wheel rotates, these vectors change. The most interesting point, perhaps, is the point at the bottom. It's instantaneously at rest. It's instantaneously at rest because the rotation about the center of mass is carrying it to the left with velocity vcm or minus vcm. The motion of the center of mass is carrying it to the right with velocity vcm, and so it's momentarily at rest. And that's what distinguishes true rolling motion from slipping or skidding. And we saw this idea earlier when we talked about anti-lock brake systems and how they work. Pure rolling is a motion in which the bottom of the wheel is instantaneously at rest. And that was why anti-lock brakes work so well, because in that case, the motion is the motion of the friction is the friction associated with objects that are momentarily, at least, at rest with respect to each other, so it's kinetic friction. So rolling motion is a sum of the motion of the center of mass plus the motion about the center of mass, and that gives us the motion of the individual points on the wheel. And there we have it. And if we look at these two velocity vectors from the translational motion and the rotational motion, they add up to give us 0, the bottom of the wheel being at rest, but only for an instant. Pretty soon that point's going to be at rest, then that point as the wheel rolls. So that's what distinguishes true rolling motion. True rolling motion has the bottom of the rolling object, the point in contact with the ground, momentarily at rest. And there are some interesting implications of that. One implication is you can see that this relationship we developed earlier, V is omega times R, that works in rotational motion also. The further away you go, the faster the point on the wheel is moving, and the central point is moving with the velocity of the center of mass, and the relationship between the rotational motion with angular velocity omega and the center of mass motion v, cm, is that v is omega times the radius of the wheel. That's true only in true non-slipping rolling motion. But we can use that to find some interesting results. Let's do an experiment. Here I have a wooden board propped up as a ramp. It's propped up on some books that I got from the teaching company's library. It's no wonder they call them the great books. They do a great job holding up the ramp. And I have two objects, a disk and a solid disk and a ring. They have equal mass. You'll have to take my word for it. They also have equal radii. Turns out none of that really matters all that much, but they have equal mass and equal radii. And these two objects are going to have a race down this ramp. And before I do the race, pause a second and see if you can figure out which one you think is going to win. Okay, placed your bets? Ready, get set, go. Solid seems to have won. And why is that? Well, let's ask about rotational inertias. The solid disk had lower rotational inertia. Why? Because more of its mass was concentrated toward the center, making it easier to change its rotational motion. The ring had all its mass concentrated at its outermost edge, like the blue one of those rods that my volunteers were shaking, it's harder to change its rotational motion. And so when these two things got going, it was harder to accelerate the ring. It was harder to give it the rotational motion it needed to get down the ramp, and so the solid one won. Another way of looking at that is in terms of energy. And since we're being quantitative in this course, let's go to the big screen and take a look at the energetics of that race between those two objects. So who's going to win this race downhill? We have these two objects. They're starting at some height h on that ramp. They're going to roll down, and they start out with potential energy at the top, U equals mgh. They had no kinetic energy at the top. I started them both at rest. Down they went. And I'm going to talk about both of them with one set of mathematics because there's only one subtle difference between them, namely their different rotational inertias. So the potential energy at the bottom I'm going to define to be U equals 0 at the bottom, so they both have U equals 0 at the bottom, and they both have kinetic energy. But the important thing here that makes this problem more subtle is they have a combination of translational kinetic energy, a half mv squared, plus rotational kinetic energy, a half I omega squared. So their total energy consists of two parts, translational kinetic energy and rotational kinetic energy. Conservation of energy says the initial energy, mgh, is equal to the final energy, which is the sum of these two kinetic energies, these two different versions of kinetic energy. So conservation of energy tells us mgh equals a half mv squared plus a half I omega squared. We can't go much further with that unless we know the relationship between v and omega. But we do know that relationship. In rolling motion, v is omega r, or omega is v divided by r. So I'm going to stick v divided by r in for omega, and I'm also going to write down that I know what the rotational inertias are. The rotational inertia for the solid disk was a half mr squared, the half coming from the fact that some of its mass was concentrated toward the center. The hollow ring had rotational inertia mr squared, where r is the radius and all the mass is distributed out there at that radius. So I'm going to write conservation of energy now as mgh equals a half mv squared plus a half. And then, just to make life easy, I'm going to write something times mr squared, because that's what the rotational inertia is. It's something I'm going to call A, and A is a half for the solid and 1 for the hollow. So that's just a way of keeping track of both of them at once. And then I've made omega be v over r, and so that's v over r squared. Work that out. The r squared in the denominator cancels with the r squared up there, so I've got a half mv squared plus a half amv squared. Factor out the half mv squared, and that's a half mv squared times 1 plus that quantity a, which is the only thing that's different between the two different objects. So there we are. Conservation of energy reads mgh equals a half mv squared times 1 plus this thing, which is either a half for the solid disk or 1 for the hollow ring. Solve this for velocity. M's cancel, as always happens with gravity, so it didn't really matter whether they had the same mass. It also didn't matter whether they had the same radius, because the radius is gone out of the picture. Solve for velocity. It's root 2gh over this quantity 1 plus a, where again, a is a half for the solid and 1 for the hollow. So downstairs, we either have 1.5 or 2. Work out the numbers. The solid ends up with a velocity which is 82% of square root of 2gh. By the way, that was the velocity we found for our skier who had no rotational energy going down a slope of height h. So if there were no rotational energy, the speed would be root 2gh. For the solid, it's 0.82 root 2gh. For the hollow, it's only 0.71 root 2gh. And consequently, solid wins, as indeed we saw happening. So that's a rather sophisticated problem involving both rotational motion and translational motion, done out fully quantitatively with these new concepts of rotational motion. Okay, let's look at one last analogy before we end. And that's the conservation of momentum. Let's look in particular at the conservation of angular momentum, because we've just seen that angular momentum is the rotational analog of linear momentum. So we have Newton's second law, F equals ma, the rotational analog, torque equals I times alpha. Newton's second law, written in terms of momentum, reads F equals rate of change of momentum of a system. F equals delta P divided by delta T. So the rotational analog of that will read torque equals delta L, the change in angular momentum per time. Torque is the rate of change of angular momentum. Force is the rate of change of regular, linear, old-fashioned MV traditional momentum. We came to the conclusion, the great big conclusion, that when a system is subject to no external forces, its momentum is conserved. If F external is 0, the momentum P of a system is conserved. Now we can draw the analogous conclusion for angular momentum. If there are no external torques acting on a system, the angular momentum of the system cannot change. The angular momentum of the system must be conserved in that case. Angular momentum is conserved, and this video clip, again looking down on the ice skater, twirling around, shows dramatically how that works. Here's an ice skater who is subject to no external torques, spinning about on the frictionless ice, pulling in her arms as she does so, and what that does is transform her mass distribution, so her mass is not way out here at the ends of her arms, but is now in much closer to her chest. That lowers her rotational inertia. But her angular momentum, rotational inertia, the analog of mass, times rotational velocity, or angular velocity, the rotational analog of velocity, that has to stay the same. And so if she configures herself differently by changing her rotational inertia, lowering it, her angular velocity must consequently go up. That's the conservation of angular momentum. There's a little richness here that we don't typically have in linear problems, straight line motion problems, because it's not easy to change the mass of something. But it is easy for a system to reconfigure itself so its angular or its rotational inertia changes, and if its angular momentum is to stay constant, then its rotational velocity typically changes. Well, the ice skater drawing in the arms is a very classic example of conservation of angular momentum. Let me show you a few other examples that are a little bit more subtle and some of them quite surprising, actually. So what I have here is a essentially frictionless platform that I can sit on. And I can make the platform rotate, and there are no torques, at least about a vertical axis through this stool I'm sitting on its rotating platform. So if, for example, I do what the skater did, and I simply spin around and then pull in my arms, I go faster. Put my arms out, and I go slower. Okay, that's the skater's thing. But here's something much more interesting. Here I've got a bicycle wheel. You can see that it's got a substantial amount of rotational inertia. It's actually got quite a heavily weighted rim, and it doesn't have much mass in between. So it's got a big rotational inertia, and I'm going to set this thing rotating. And I'm going to sit on the stool with it, and here it is rotating. Now the system consisting of me and wheel has angular momentum. And now it has angular momentum in the opposite direction because I turned the rotating wheel around, and look what happens. I spin the other way. And if I want to stop, I just flip it back. The system's angular momentum remained the same the whole while, except for the fact that the wheel was eventually spinning down. Why did the system's angular momentum remain the same? Because angular momentum is conserved. There were no external torques acting on the system to change its angular momentum, and so the angular momentum remained the same. What happened was, at one point the wheel was spinning in one direction, so its angular momentum was one way. I reversed that angular momentum, and in order to keep the angular momentum what it initially was, I had to spin in the opposite direction. The angular momentum stayed the same of the whole system, but different parts of the system changed their angular momentum, and that's what happened when I turned this wheel over. I can do something else with this wheel, which is a little more startling. I have to wind up this string again. And I'm going to take another piece of string, and I'm going to clip it onto one end of the axle. And I'm going to spin the wheel again. And I'm going to suspend the wheel. And lo and behold, instead of falling over, it goes round and round and round and round and round and round. Why on earth is it doing that? Well, it's doing that because it has some angular momentum. The angular momentum happens to be, if you want to give it a vector direction, pointing out along that shaft, and there is a torque on it. The torque is due to the gravitational force, which, if the wheel weren't rotating, would make it simply fall over. But because it's rotating, there is a torque in a direction which tends to make it rotate. It would also rotate, it would also tend to make it rotate even if the wheel weren't spinning. It would just rotate downward like that. But because the wheel is spinning, the direction of the angular momentum vector changes in a way that takes the wheel around. That's a phenomenon called precession. I can illustrate it a little better with this gyroscope I have over here. Here's a carefully balanced gyroscope. Consists of a massive disc with a lot of rotational inertia. I've got a string on it. I'm going to set it rotating. There it goes. It happily sits there. And now I'm going to hang a small mass from one end of it to imbalance it. Now there's a gravitational torque acting on it, changing its angular momentum. And its angular momentum, it turns out, if you try to express these things in vectors, is a vector that's pointing along the axis of rotation, and it's that vector that's changing in response to the torque. And just as Newton's law is about systems changing their motion in the direction of the force, not moving in the direction of force, but changing their motion in the direction of force, so Newton's law analog is about rotating systems changing their angular momentum in the direction of the torque that's acting on them, and that is exactly what's happening here. There's a big example of that we're part of, and that's the precession of the axis of rotation of our own planet Earth. Earth is not quite a sphere. It's actually kind of oblate. It sticks out a little bit more at the equator, and there are torques associated with with the sun's gravity acting on different parts of the Earth, and they cause the planet to precess more or less like a top, more or less like my gyroscope, because of those torques that are acting on it. And the precession period is about 24,000 years. That means today, the north polar axis of our planet points at Polaris, the North Star. 12,000 years later, it will point in quite a different direction and come back again another 12,000 years, 24,000 years hence, and again it will be pointing to Polaris. 24,000 years is a pretty long time. That's a pretty slow precession. We believe that that effect is one of the major effects responsible, for example, for the ice ages. I show a plot of temperature over the last roughly 500,000 years, and it shows these very periodic cycles of the ice ages, and we believe those ice ages are triggered, not entirely caused, but triggered by astronomical changes like the precession of the Earth's axis through space, in the direction of the Earth's axis in space. Rotational motion is a fascinating topic. I haven't really done justice to all of it in this lecture, but let me just wrap up with a summary. First of all, rotational motion is described by quantities completely analogous to those for linear motion. There's an analog of Newton's second law that relates torque to rotational inertia and angular acceleration, and conservation of angular momentum leads to a wide variety of sometimes startling phenomena, like particularly the phenomenon of precession.